Let's study 10th Standard ICSE Physics, Chapter 7 Sound, Section B and C, that is Resonance and Characteristics of Sound. Now, vibrations are of three types: natural, damped and forced vibrations. And vibrations produce sound. Natural vibrations are periodic vibrations of a body in the absence of external force on it. So they are called free vibrations because they are perennial. They will never come to a stop. So practically that's an impossibility. But an approximate example would be a pendulum swinging in vacuum. It will keep on vibrating periodically in the absence of an external force, because once we set it in motion, it would continue to do so. Of course, there will be some gravitational force acting on it. And there is vacuum, so there is no air resistance to slow it down, although there will be some friction at its point of suspension. Another example would be a guitar string set into vibration in vacuum. Of course, we won't be able to hear any sound, but that would be a good example of an almost free vibration. Some other examples would be a tuning fork, which is vibrating in the absence of any air resistance, of course. And it will produce a sound of a single frequency, which is called its pure note. You see, any substance in the absence of an external force would vibrate when struck. It would vibrate at its natural frequency. So if the tuning fork's natural frequency was, let's say, 256 Hertz, then if you strike it, it will start vibrating at 256 Hertz. And indeed, the sound produced by it will also be of frequency 256 Hertz. When you blow air in a flute, then sound is produced again. And the frequency of the sound, that is the note produced, depends on the effective length of the air column which is vibrating. You see, by closing different holes, you are changing the length of the air column vibrating in it, which affects the frequency of sound produced. Remember, more the length of air column vibrating, less is the frequency. Now, look at this diagram which shows different modes of vibrations in a string. Here the string, let's say, of a guitar was plucked, and here it's the first subsidiary note, and here I see it's a second subsidiary note. I can see that the wavelength of the vibrations is decreasing. You see, you can change the length of the guitar string vibrating by keeping your fingers at particular positions and then plucking it. Let's understand the ratio between the wavelengths out here. Let's assume this length is L. So wavelength is the length of one complete wave, but this is only half a wave, you see. So if I complete it, it will be L plus L, 2L. So its wavelength is 2L. Here the wavelength of one wave, this is one wave. I'm not talking about this corresponding wave here. The wavelength here, this is one complete wave, so that is L, exactly L. Okay, so 2L upon 2 is actually L. What about this? Well, I see 1.5 waves out here, 1.5 waves. So its wavelength is 2L upon 3, that is 2/3 of L. This is entirely L, and this much is one wave from here to here, that is 2/3 of L. Now if you take the ratio of these three, L gets cancelled, and you get, after LCM, the ratio is 6:3:2. So that's the ratio of the wavelength in this case. If we were to plot a displacement time graph for the free vibration, it would look something like this. I can see totally 1, 2, 3, 4, almost 5 waves. And the amplitude, that is the maximum height, the maximum displacement of the particle of the medium from the mean position, the amplitude remains constant. That is, the intensity of the wave will remain the same. It will go on forever, but that's an ideal condition. The reality is that the energy decreases, the amplitude keeps on decreasing, and the wave stops, the vibration stops. Imagine a ball which you release from a height, it hits the ground, then it rises again to a certain height, again it falls down and hits the ground, and so on. But will the ball keep bouncing forever? No, its height will keep on decreasing and ultimately the ball will come to a stop because slowly its energy, its kinetic energy is getting converted into heat and sound energy because of friction with the air and with the surface of the earth. So such practical vibrations are called damped vibrations. This is the reality of all vibrations. The periodic vibrations of a body of decreasing amplitude in the presence of a resistive force. There is a resistance, we can't escape that. That resistive force can be due to friction with air or water or any other medium. Such vibrations are called damped vibrations. Examples, well, you can give any example which you mentioned earlier, but don't mention the word vacuum. For example, if we pluck a slim branch of a tree, if we pull it, then it will vibrate for some time and it will come to a stop. Or even a tuning fork will vibrate and then come to a stop because it is getting damped due to the air resistance. Even a simple pendulum actually oscillates in air, and that is a damped vibration. So these are the differences between natural and damped vibrations which need to be studied. Remember, the frequency of vibration never changes. So even here, even though the amplitude is decreasing, the frequency of vibration remains the same. If it was making 5 oscillations per second earlier, then even though its amplitude is decreasing, it will continue to make 5 oscillations per second. In natural vibrations, there is no loss of energy, but here there is a loss of energy in the form of heat. But what if I want the pendulum to go on forever? What if I want this vibration to go on forever despite the frictional force acting on it? Despite the resistive forces acting on them? Well, then you'll have to continuously apply some energy to it. You'll have to continuously apply some force at regular intervals to keep it in motion. That's how a pendulum can stay in motion forever, if you have an external force acting on it periodically, and that is called forced vibrations. The vibrations of a body which take place under the influence of an external periodic force, because the moment you stop applying this periodic force, after some time this vibration will come to a stop. So as long as you keep applying this external periodic force, the force vibrations can be sustained for a long time. So there are 3 types of forces acting in such force vibrations. The restoring force, that is, if you release a pendulum from one end, there is a restoring force trying to get it back to the mean position. Then there is a frictional force which resists its motion, that is usually by air. And then there is an external periodic force. Let's say if the pendulum is oscillating and you keep pushing it after regular intervals, then the pendulum will keep on oscillating. It's like the swing. If a child is sitting on a swing, you have to continuously push it again and again so that the swing does not stop automatically. So that's an example of a forced vibration. However, understand that you have to time the force applied on the swing. If the swing is oscillating at a particular frequency, even you need to use your hands and push it after fixed intervals of time. If there is a mismatch between the force frequency, the frequency of the force which you are applying, and the frequency at which the swing is swinging, then the swing will not oscillate with maximum amplitude. Let's take another example. When the stem of a vibrating tuning fork is pressed against the top of a table, then the tabletop is also set into forced vibrations. Now when you hit the tuning fork, it started vibrating freely at, let's say, 256 Hz. That was its natural frequency. But when it came in contact with the tabletop, it is forcing the tabletop also to vibrate at 256 Hz, even though the tabletop is undergoing forced vibrations. So the amplitude of vibration would be less. The sound produced would be quite large, but it could have been larger had there been resonance. We'll come to resonance in a bit. But first of all, why is the sound produced by a tabletop more than that produced only by the tuning fork? Well, that's because the tabletop has a larger surface area. And more the surface area, louder sound is produced. That is why when you ring a large bell, it produces a louder sound because there is more surface area able to vibrate. Even in a stringed instrument, there is a hollow sound box containing air. If you've seen a guitar, an acoustic guitar, you may know that there is a hollow in it. Have you ever wondered why is there a hollow in this? And of course there is air inside. That's because when you plug the strings themselves won't produce very loud sound. But these vibrating strings will cause forced vibrations in the air inside the guitar's hollow. And these forced vibrations of the air will produce a loud sound because the surface area of vibration is increased now. So now you know the difference between natural and forced vibrations. In natural vibration, there is no external force acting, but in forced vibrations, an external force is acting. Here, the frequency of vibration depends on the shape and size of the body itself. Every object has its own natural frequency, whereas here the frequency of vibration depends on the frequency of the applied force. Here the frequency remains constant, and here the frequency can be changed depending on the applied force. Here the amplitude remains constant, assuming that it is in vacuum. And here the amplitude actually depends on the frequency of the applied force. If the frequency of the applied force matches the natural frequency of the object, then the amplitude is maximum, and such a special case of forced vibration is called resonance. That's right, resonance is forced vibration. There is an external periodic force forcing the object to vibrate, but now if the external periodic force's frequency matches the natural frequency of the object, then the object will vibrate with maximum amplitude, and that is called resonance. That means if you are applying a force on the swing on which a child is sitting, and you are timing the application of the force with your hands to the swing, such that the frequency of the force you are applying matches the frequency with which the swing is swinging, then the swing will swing with the maximum amplitude, which might be quite scary for the child. So resonance is defined as a special case of forced vibrations when the frequency of the externally applied periodic force on the body is equal to its natural frequency. Then the body readily begins to vibrate with an increased amplitude, and this phenomenon is known as resonance. Now the condition for resonance is that the applied force causes a force vibration in the body, and the frequency of the applied force is exactly equal to the natural frequency of the vibrating body. Let me give you an example. You may have seen an opera singer who's able to break glass with her voice. You see, when she sings and the sound carries the vibrational energy everywhere, even to the glass, and even the glass will start vibrating. And that is a forced vibration. If she could match the frequency of the natural frequency of the glass, then the glass will vibrate with such a maximum amplitude that it shall break. Something like this. So here's an assignment for all of you. You need to do this experiment at home and keep trying till you break a glass with your voice. In the name of science. Resonance. Let's take another example. Suppose we have a tuning fork A. We set it in vibration with its natural frequency. We keep it on a sound box which is facing another sound box. So the vibrational energy can be transferred with the help of air. And you will notice that this tuning fork, even though it is not in contact with it at all, also starts vibrating. In fact, it will start vibrating at the same frequency as this one, because both of them have the same natural frequency. And a very loud sound will be heard because the frequencies match and the amplitude of vibration is maximum. This is an example of resonance. In this example, we have this rubber string and we have 4 pendulums these 4 weights A, B, C, D are hanging. Notice that pendulum A and B have the same length, and as you know that if the pendulum's length is same, then the frequency is also the same. Set the pendulum A in motion, give it some energy, give it a push, so it starts oscillating like this, in and out. This energy is transmitted with the help of this rubber string to all the remaining pendulums, and so even they will start swinging. C and D will swing less, and they will come to a stop after a short time because that's a forced vibration with low amplitude. But since the frequency of B and A are matching, resonance will occur. B will start oscillating with greater amplitude. In fact, A and B will be in sync. If A goes left, B will go right, and so on. Slowly, all the energy of A will be transferred to B, and finally A will come to a stop, whereas B will oscillate with maximum amplitude, just like A was in the beginning. Here's another experiment which can be performed at home, and in fact it is a part of practicals in college physics. You have this beaker with a scale. You have water up till a certain level. You can change the water level with the help of this container. You keep a vibrating tuning fork on top of it, which will force vibrations in the air column between the tuning fork and the water level. So you will hear a sound. Now keep decreasing the level of water here. You will notice that at one particular length, a very loud sound is heard. So what has happened is a resonance. You see, as the length of vibrating air column is increased, its frequency of vibration will decrease, and when that frequency matches the frequency with which the tuning fork is vibrating, sound of maximum amplitude is produced, which is called resonance. Mark that level. Now continue decreasing the water level. Again, since you have changed the length of the air column, its frequency of vibration will change. So now there will be a mismatch between the vibration of the air and the frequency of vibration of the tuning fork. So now there will be no resonance. It will just be a forced vibration. So sound will be produced, but not as loud. But when the length of the air column becomes 3 times the previous length, yes, 3 times, again you will hear resonance, because once again the frequency of vibration of the air column will match the frequency of vibration of the tuning fork. Why when the length is 3 times, that you need not know, but it's just an observation of a resonance in air column. So now you know the difference between forced vibration and resonant vibrations. Yes, in both the cases there is an external periodic force, but here the frequency of the external periodic force matches the natural frequency of the body. So remember that resonant vibrations are just a special case of forced vibrations. And here the amplitude is quite small, and here the amplitude is very large. Here the vibrations will last for a small time. As soon as the periodic force is stopped, it will stop vibrating soon. But here the vibrations will last for a long time, even after the periodic force has been stopped. Now there are some applications and uses and examples of resonance. Have you ever heard a buzzing sound in some machine like your AC? Suddenly it starts producing a loud sound, or even your vehicle, your scooter or your car, a part of that machine starts making some vibrating sound. What may have happened is that while you were driving, the piston of the engine, which keeps oscillating in the machine, what if the frequency of that piston of the engine matches the natural frequency of the metal part of your machine? Then that metal part of your machine or your vehicle will start vibrating with maximum amplitude because of resonance, and you will hear the sound. This is true for any machine, even a washing machine or an AC or a refrigerator. Resonance happens. And this rattling sound may be quite irritating. The solution is very simple. Just create a mismatch in the frequency. But how do we do that? Well, as far as a vehicle is concerned, just change the speed of the vehicle. Either increase it slightly or decrease it slightly, so that the frequency of the piston will change, and now it won't match exactly the natural frequency of the vehicle's frame, and so resonance won't happen. Resonance is also used in musical instruments. Musical instruments may have a sound box which has air in it, just like the guitar had that sound box in it, that hollow. hoping that the frequency of vibration of the strings, the vibrating strings, may match the natural frequency of the air in the sound box. Then resonance will happen and a very loud sound will be heard. Resonance in a bridge can also happen, especially if it's a suspension bridge. Not a bridge made up of steel and cement, just a suspension bridge made up of wood and ropes. It's possible that the bridge may break due to resonance. What if the soldiers are marching perfectly, rhythmically on the bridge, and the frequency of their march matches the natural frequency of the bridge? Then the bridge will start oscillating, it will start vibrating with a large amplitude, which can be quite risky. That is why the soldiers are asked to break their steps. That is, they are not allowed to march in unison, in sync, while crossing a suspension bridge. Then in radio and TV receivers, have you ever wondered that when you change a channel on radio, when you go from 93.1 megahertz to 98.1 megahertz, how does the channel change? What is the mechanism behind it? Even in a TV, when we switch the channel from one to another, how does it pick up the radio waves of some other show automatically? Well, what happens here is that the TV receivers and radio receivers have electronic circuits which produce electromagnetic vibrations. So here we're not talking about sound, okay? We're talking about electromagnetic vibrations here. And we can change the frequency of these electromagnetic vibrations by changing the values of the electronic components. That is, just switching the numbers, changing the numbers, the channel number with the help of the remote. So when we switch or change the station of a TV or radio, then it starts vibrating at a particular frequency. Now, radio waves of various channels and various stations are already present all around us. It's invisible, but it's there all around us. All we need to do is catch it and listen to it. So when the electromagnetic vibrations frequency matches the frequency of a particular channel or station, a resonance happens. So the electrical equipment is now able to pick up that particular station, amplify it, and convert the signal into audio visual output. And so we can see and hear that channel. The detailed electronic components are not there in our syllabus. We just have to know that this is based on a principle of resonance. And again, this has nothing to do with sound here. It's actually related to electromagnetic waves like radio waves and microwaves. We can visualize the waveform of sound using the CRO device, which is cathode ray oscilloscope, so that we can see the graph of the vibration producing the sound. Sound is not a transverse wave like that. Sound does not have crests and troughs. It's just a graphical representation to help us understand its features. And we shall study three characteristics of sound now: loudness, pitch, and timbre. First of all, loudness. Loudness is that characteristic of sound by virtue of which a loud sound can be distinguished from a faint one, assuming that both of them have the same pitch and quality. So even if the pitch and quality are same, still we can distinguish between loud and soft sound because of this characteristic property called loudness. What is pitch and quality? We'll come to that later. But to understand loudness, let's see this graph. Sound with a larger amplitude will produce a louder sound. So loudness depends on amplitude. More the amplitude, louder is the sound. Don't use the word directly proportional yet. Actually, intensity of sound, that is the amount of energy or sound energy passing per second through a unit area normally. So the amount of the intensity of sound depends on the amplitude, and then the loudness depends on intensity of sound. So indirectly I can say that loudness depends on the amplitude of sound. Mathematically, loudness is proportional to the square of the amplitude. So if the amplitude doubles, loudness will quadruple, and so on. So that was the first factor affecting the loudness of sound. There are some other factors also which affect the loudness. It depends on how far the source is. The farther away the source of sound is, the fainter is the sound. it is inversely proportional as the square of the distance of the source. So if the source is twice as far away, then the loudness will become 1/4 of the original loudness. Third factor, it depends on the surface area of vibrating body. More the surface area, louder is the sound. We have studied this example where a tuning fork was struck and kept on top of a tabletop, and since the tabletop has a larger surface area, a louder sound was produced. That is also the principle behind sound boxes being used in musical instruments, to provide a larger surface area for vibration. The fourth factor is the density of the medium. More the density of the medium, louder is the sound. And finally, it also depends on the presence of resonant bodies. If there are some objects whose natural frequencies match the frequency of the sound, then even those objects will vibrate with a large amplitude, increasing the loudness of the sound. On the other hand, if there are some objects like curtains and rough surfaces which absorb sound, then the loudness will decrease. But understand that loudness is a subjective property. So it differs from person to person. For some people, a particular sound may be loud, but somebody else may say it's not that loud. Intensity, on the other hand, can be measured. It has mathematical units. It's an objective property. Everybody will get the same answer. But loudness is a subjective property. Now, if, for example, there is a music. Now, a particular music, some people may find it to be quite melodious and pleasant, but on the other hand, some people may find such silly music just loud noise. Now remember, the unit of loudness and sound level are different. For loudness it is phon, and for sound level, for level of sound, it is decibel. Now, what's the technical difference between them? That is not in your syllabus, so you don't have to worry about it. Just learn the units. Noise pollution, well, any sound above 120 decibels is definitely contributing to noise pollution. In fact, a constant hearing of above 120 decibels can cause headache and permanent damage to the ears of the listener. The safe limit is 0 to 80 decibels. That's perfect. In fact, 30 to 10 decibels has a soothing sensation, and 0 decibel represents the lower limit of human hearing. It does not mean zero sound. It's just a subjective property for us. Below 0 decibels, we can't hear the sound. This is the limit of hearing. Here we are not talking about the audible range of sound. That is 20 hertz to 20,000 hertz. That's a frequency of sound which we can hear. Whereas decibel is a measurement of the level of sound. The next characteristic is pitch. Now, pitch is that characteristic of sound by which an acute or a shrill note can be distinguished from a grave or a flat note, assuming that both the sounds have the same loudness and quality. So the best way to visualize it is using the graphs. Here you can see that the frequency is more compared to this one. So this will be a higher pitched sound, a shrill sound, and this will be a grave sound, a treble sound, a low pitched sound. Usually males have a low pitched sound and females have a high pitched sound. Now, high pitch does not mean loud sound. There is no connection between loudness and pitch here. Loudness depends on amplitude, whereas pitch depends on frequency. Here you see the amplitude of both the waves is same, so the loudness is same for both of them. Now, one give reason is if you have a bucket under a tap which is being filled with water, as the water level rises, even though you're not watching it, you do realize somehow that the bucket is full of water, or it's about to get filled with water. That's because the frequency of sound changes. You see, when the water level was here, the length of vibrating air column was so much. But as the water level rises, the length of the vibrating air column between the tap and the surface of water decreases. That means the pitch or the frequency increases, and because of the high-pitched sound, we realize that the bucket is about to get filled. Make sure you write whatever is added here. Again, pitch is a subjective property, and frequency is objective, because frequency can be calculated in hertz, whereas pitch, well, everybody has a different perception about it. For you, some sound may be high pitched, but for me, it might not be so high. It may be a low pitched sound. Finally, the quality or timbre. It is that characteristic with the help of which we can distinguish between two sounds, even though they have the same loudness and pitch. For example, look at these two sounds. They have the same number of waves, so same frequency, same pitch, same amplitude, so same loudness, and yet when you hear them, you can distinguish between them because the quality of sound, the timbre of sound is different, which can be seen in the representation of the wave. Even here, this is a simple sound produced by a tuning fork, and this is a more complex type of sound produced by a piano. The wave form is such because it is actually multiple waves which are overlapping on top of each other. It's a superimposition of a few vibrating parts of the piano, and the combination of all these primary and secondary, that is subsidiary waves, together give this peculiar blue wave pattern. That's why the piano has a very distinct sound compared to other musical instruments like the guitar or the flute. And that is why even though the amplitude may be the same, that is the loudness is same, and even the frequency is same, the number of waves per second is same, so pitch is same, and yet we can distinguish between different musical instruments. We can distinguish between the voice of different people because each has a unique timbre, a unique wave form. And finally, the difference between music and noise. Again, that's very subjective because some song may be musical to you and it may just be noise for me, and vice versa. But more or less we can conclude that noise is just unpleasant and random waves, whereas music is regular, smooth and pleasant to the ear. It has periodic waves, whereas there is irregularity in these waves. Usually noise is very loud, more than 120 decibels, whereas music is supposed to be between 10 to 30 decibels. Now you need to solve these numericals here, which are quite straightforward based on the concepts that we have studied. For example, here they've asked us to find the ratio of the wavelength. If you notice here, if I take this much as x distance, then it has 1.5 waves. That means one wave here, this is x distance, 1.5 waves. So one wave is 2/3 of x. So the wavelength here is 2/3 of x, whereas here one wavelength is x. So this is 2/3 of x wavelength, and here the wavelength is x. So the ratio is 2/3 x upon x, which is 2:3. Now remember that loudness is directly proportional to the square of amplitude. So since the amplitudes were given, we could find the ratio of the loudness.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.